So let's say we have this reaction. So let's say we have this chemical reaction. Which side is the products?
Right side.
Which side are the reactant?
Left.
Okay, is it balanced? And what do I mean by that?
If each element has the same amount of atoms in the reactants and the product side.
No, it's not balanced.
So it's not
That's
balanced.
not balanced.
Okay, what are the atoms in this reaction?
We have carbon,
Okay.
Hydrogen,
oxygen,
and oxygen.
Hydrogen.
and oxygen.
Okay.
Yeah,
Okay. On the reactant side, how many carbon are there?
1.
one,
On the product side, how many carbon are there?
one,
How many hydrogens are on the reactant side?
4.
5.
5?
wait, okay, 4. Okay, it's 4.
4?
Yes,
And then on the
2.
product side,
that's 2.
how many oxygens on the product side?
3. Oh, yeah, 3.
And on the reactant side?
3.
Okay, is it balanced?
No,
No,
Okay. so
hydrogen.
balance it.
we add 2 in front of H2 to make hydrogen 4.
So you're saying put a 2 in front of the H2O.
Yes,
That's what I heard.
yeah, yes, that's it. That's what I said.
A 2 here. What is that number? That 2. What is that called?
Oh,
Exponent? Oh, no.
forgot.
Whole number?
It's the
It is a
coefficient.
whole number, but that's not what it's called in this case.
Coefficient.
Coefficient. That's right. This is called the coefficient.
Yeah.
Okay. So what is this called? This number that's down here.
Subscript.
Subscript. Okay. So how many hydrogens do I have on the product side?
You have 2.
You have
I have
2.
2. I have 2.
Yeah, you have 4 now.
Oh, 4.
I have
Now.
4.
Now, yeah.
Yes.
Okay. So now I have 4. So my hydrogens are balanced, but how many oxygens do I have?
You have more now. You
Now
have 3.
you have 4 on the product side and 3 on the
4.
reactant.
You have
Yes.
4.
I have
4 now.
4. Okay. Yeah. 'Cause
Yes.
I have the 2 here, and this
Mhm.
coefficient means that
Yes.
I have 2
Times 1.
times 2 hydrogens and 2 times 1
Times
because it's
1.
understood to be 1, right?
Mm-hmm.
Okay. So now I
Yes.
have a total of 4 oxygens. Is that balanced?
No.
Yeah.
Oh,
Okay, no.
so would you have put a 2 up here on the reactant side in front of the O2 so that, no, because then you'd be over. What a
So if I
mess.
put a 2 here, then I'd have,
You have
You
5.
have-
oh, damn. This is going to be a little bit hard, isn't it?
Mhm.
Ugh.
I think you need to disturb carbon a little.
I need to what?
You need to disturb, as in, you need to put some mess up with the CH3.
So I'm going to have less with that C, right?
Yes.
Somebody has something.
Uh-huh. So let's see.
Okay.
Mhm.
So let's see. So if we, let's say if we put a 2 here.
Mm.
Right. So, but right now, everything is pretty good, right? Would you guys,
Mm.
you agree that everything is kind of good right now? Yeah.
We'll need to try.
We have one carbon, technically one carbon, we have 4 hydrogens. The only thing now we have
Oh.
five oxygens, right? So let's see what we can do to kind of fix this.
Mhm.
I'm going to show you guys a little method.
Yeah.
So if we take a look at this, we have 1 oxygen here, and we have, this guy has 2.
Right.
Mhm.
Now this is going to be real quick, and you guys are going to yell at me a little bit, and then I'm going to tell you why you can't have a half of a something, but it's going to work out, and it's going to work out to our favor. So we need a total of 4. That's correct, right?
Yeah. So
Okay. So if I take this 4, I subtract that 1 that's in this complex. How many would that leave me with? So 4 minus 1,
3.
3. Okay. So if I set 3 divided by 2, and I put 3 halves here. Oops. Three halves times 2 is what?
3. That's 3.
So 3 plus 1, how many is that?
4.
4.
Okay. So would that be balanced?
Yeah.
Now do I have 4?
Mhm.
Okay.
Yeah.
So this is one way that we can learn how to balance equations. But the problem is that, can you guys have a half of an atom or a half of a molecule?
No.
No, we can't.
No.
So we want to get rid of that fraction. The way that we would get rid of the fraction is to multiply by 2. Right? Multiply the whole reaction by 2. So that means that we, at the end of the day, we'll have 2
Oh my god.
And I always like to verify. Verification is always very important. You have time to do it. So how many carbons do I have on my reactant side?
You have
2.
2.
Well,
How many carbons do I have on my product side?
4.
4.
2. 2.
2.
2.
How many hydrogens do I have on my reactant side?
4.
That's
3 plus 1 is 4
7.
times 2.
Oh,
Eight.
I forgot. Sorry. Yeah.
8.
Right?
Yes.
Yeah.
And then on my reactant side, I mean on my product side,
8.
8.
and then how many oxygens do I have on my reactant side?
3.
8.
6.
Oh,
Oh, 8.
3 times 2.
2 is what?
6, 7.
6.
Plus 2
8.
is 8.
8.
9.
20.
Okay.
No, I'm just kidding.
Wait, I messed up. Wrong math.
Can you count?
I see, wrong math. Okay, you guys see?
Can you
that
tell me
eight?
how you counted the oxygen again, please?
Okay, because the coefficient is multiplied by whatever number's here. This is understood to be a 1. There's an oxygen here, is there not?
Right.
Okay, so 1 times 2 is what?
2.
2.
And then over here, we have 3 times 2.
Okay, 6.
And we add it together.
8. Oh, okay. So you're kind of treating them as two different equations, but at the end you add them together, right?
That is correct. You want to find out independently, and then you bring it together, because all together, it's what you put in all together, what you get out all together. Okay? So how many oxygens do we have over here? Start over here with the CO2.
It's 8. Oh, well, 2 times 2 equals 4, then 4 times 1 equals 4, so it's 8.
2 times 2 is equal to 4. 2 times 2, and then 4 times 1. We add them together. Simple.
Yeah.
Yeah.
I heard somebody talking about PEMDAS. I mean, PEMDAS. Okay. Pretty simple, right? Are you feeling it?
Yes.
Okay, good.
Can there be like multiple different answers that different people can come up with, or would it always end up the same?
No, you should always end up the same. There are not multiple answers. There's one answer. That's it.
Okay.
Okay.
Dr. Henry, are we gonna do another question like this, or are you just gonna move on?
I'll do one more. If you are you asking me to do one more? Is that what you're saying?
Can we please do one more, please?
Can we please do one more? So that
Yeah.
yes, we can surely do one.
One more, please.
Okay. But if you don't say anything, I will gladly go forward. Let's see. Let's do. So just for the record, this type of reaction, anytime you have carbon and oxygen by itself, like a carbon molecule, and oxygen by itself, like oxygen gas, those are called combustion reactions. You don't need to know it yet, but I'm just giving you a heads up. Okay? So the product is going to be, in combustion reactions, it's always going to be the same, unless you're doing things which does happen. But it's always going to be carbon dioxide and water. Okay, so looks pretty easy, right? This one should be a piece of cake. Strawberry chocolate cake. Okay, where should we start?
Carbon on the left.
Okay, carbon on the left, is that the products or the reactants?
That's the reactant.
Yeah.
Okay. How many carbons do we have?
2.
2.
2.
Okay, on our product side.
1.
Okay, on our reactant side, hydrogens.
6.
6.
6.
On our product side,
2.
2.
on our reactant side, oxygens.
2.
2,
2.
On our product side, oxygens.
3.
3.
Is it balanced?
No.
No.
Okay, so what do I need to do?
Balance it.
I love that. Hey, so what do you mean by that?
Can add a 2 in front of CO2.
Put a number in front of CO2. What number are we going to put in
That's
front of
2.
CO2? A 2.
2.
Okay, so we're going to put a 2 in front of CO2.
Yeah.
Mhm.
Okay, so how many carbons do I have now?
2.
2.
Or 2, sorry.
Okay. How many oxygens? Because oxygens are changing over here now.
4. 5.
5.
5.
5, right? Because you guys, it's 2 times 2, so that's 4, plus this one over here.
Yes.
Okay, is it balanced?
Nope.
No.
Okay, so what do I need to do next?
You need to balance the
Hydrogen You could add 3 in front of H2.
Add 3.
In front of which
In front-
hydrogen? There's a lot of hydrogen.
H2.
Product
H2.
On the reactant side or the product side?
Product.
Product.
Side.
On the product side. So you're saying put a
Yeah.
3 in front of this hydrogen,
Yes.
okay? So then that
Yeah.
gives me how many hydrogens?
6.
6.
Six.
And that gives me how many oxygens?
4.
That gives you
No.
Wait.
7 on the product side.
7.
7, yeah, 7.
Okay, is that balanced?
No.
No.
Okay, what do we need to do now?
Could do that fraction thing.
Do that fraction thing. So do we have any oxygens over here?
Yeah.
Yes.
Yes.
O2.
I mean, in
Could
this,
do the
in this.
No, not on that side. No.
Okay, so
No,
I'm
not
right
in
on
the
that.
O2. Yeah.
Okay, so how can I end up with 7 if I have 2 oxygens here?
Times by 7 over 2.
If I multiply this by 7 over 2.
Yeah.
So do you
Okay.
always make the denominator the same as the coefficient?
If you need to, right? If it's an odd number,
Yeah.
yeah, you don't have to do
Yeah.
it that way. But if it's an even number, right? If it was 8 on
Mm.
the other side, then we don't have to do it that way, right?
Okay.
Yes.
Okay.
Yeah.
So in this case, yeah, you want to, because you want to cancel it out, because you know that if you multiply 2 times 7/2, what does that equal?
7.
7.
14.
That equals 14?
The
14.
2
That's
cross
7.
elimination.
7.
Yeah, these guys are going to cancel each other out, and you're just going to end up with 7.
Yeah.
All right. Come on, you guys, basic fractions. Okay. Okay, simple. Are we done?
The
No, we're not
simplest.
done.
No.
So what do we need to do?
Multiply
Multiply
everything
everything
by
by
7.
Multiply everything by 7?
Oh
No,
no,
but 2.
multiply it by 2. My bad.
By 2, because we want to get rid of the fraction, right?
Yes.
Okay.
So 2 times 1 is what?
2.
2.
2 times 7/2
Is 7.
2 times 2,
4.
2 times 3.
6.
Dr. Henry, is there a faster way to do this? Or do we have to keep on doing it until we get to an uneven number?
What do you mean by an uneven number?
Like, you know how we kept on doing the basically trying to get everything even until we got to the uneven number, which was 7, and then we had to do the fraction.
I'm not sure exactly what you're trying to ask me, but the fastest way, this is actually the fastest way.
Oh, okay, this is the fast one.
Yes, right? And you could guess, but you just want to be sure. Now, the thing is that you want to make sure that the numbers are the lowest they could possibly be. If you could divide everything by 2, let's say you had a 14 here. Let's just say for kicks and giggles, there's a 14 here, 7. Then you had 2, 14, 4, and 6. That means that you made a mistake somewhere, right? Because you want it to be the lowest possible whole number you can get. Okay? Does that make sense?
So you're only multiplying the new addition, like the new numbers you've added in there, which would have been the 7/2, the 2, and the 3, but the others all stay the same.
No, you need to we multiplied everything by it because you have to do that to the whole equation. Does that do you understand?
Oh, I get it. No, I don't. Well, yeah, I mean, I was following along, but then I got lost. Because it's 2 times
2 times 1, 2
uh-huh.
times 7/2, 2 times 2, and 2 times 3.
Right.
Multiplying the 2 is just affecting the coefficients, not the subscripts.
Thank you. Okay,
That's
that's
right. So that's what you're asking. Yeah.
yeah.
So you never, like once you know the chemical, what the chemical is, you never want to change the the subscripts, because then that means you're changing the chemical. So if you wrote this, let's say we had this chemical, C4H12. These are two different chemicals. Do you understand? So C4H12 is not the same thing as C2H6.
Okay.
Okay, they're not the same. Okay, in this compound there are 4 carbons. In this compound there are 2 carbons. They will behave differently. They will boil at different temperatures, right? This guy will boil faster. Actually, this guy won't even boil. It's actually a gas. This guy is a liquid, but liquid gas at room temperature. So they're going to be different.
So you don't touch the original compounds and only the new additions to what we added prior, the coefficients?
You
or-
only change the coefficients, yes.
And-
That's why it's important that you guys learn those terminology. You don't
Yeah.
want to touch the substance. Once you know the chemical, now there are going to be cases where you're going to have to try to predict the outcome. Let's say you have the reaction, they'll give you your 2 starting things, and they'll want you to predict what the products are. That's going to be different. And then we'll talk about how you would go about that process. Okay, because there's a pattern. Okay.
Dr. Henry.
Yep.
So basically, once you balance the equation, there should always be an odd number as a coefficient. Is what you're saying?
Yeah. If all your numbers are even, then you did something wrong. Let's say all your coefficients are even. So this is a 2, this is a 14, this is a 4, and this is a 6. Then you did something wrong. You should have at least one number that's an odd number.
Okay.
As a coefficient.
And what's the idea behind it? How come again?
Because you want to try to make the chemical equation the simplest as possible, right?
Okay.
Because you're thinking about this is like a recipe, right? So if you're baking a cake and it says you need 1 cake mix, right, for 3 eggs and 1 cup of water. Oops, I don't know what I was writing there. Say water, okay? I know this is it. I know we're missing our oil and all that stuff, but we're going to say that's going to equal a cake, okay? Now, that's a yield sign, okay? So if I want to make 1 cake, and let's say you went through and you told me that I need 2 cake mix, 6 eggs, 2 waters, and that equals 2 cakes, right? So my intent would be is like, I only want to make 1 cake. Why do I need to sit there and buy 2 cake mix, 6 eggs, and 3 waters, right? You want to make it as simple as possible. Otherwise, people get confused, right? And you want to keep it as simple as possible. This isn't as simple as possible. You just basically told me I need to buy all of this stuff because the first thing I'm going to do is look at the recipe, say I need 2 cake mixes, I need 6 eggs, and I need 2 things of water. And I'm going to only want to make 1 cake. So when I do that, I'm not making 1 cake, I'm making 2 cakes. So when I put it in my pan, I'm going to just pour all my 1 cake mix and then I fucked up, right? Because then it's all flowing over. Do you understand?
Mm-hmm.
So do you see the logic, Heather?
Yeah.
Yeah. So you want to try to keep it as simple as possible, simplest way as possible. Because to be honest, sometimes we don't use our common sense when we're in the kitchen or we're in lab, right? And you're just going to follow the recipe because that's what the recipe said. Do you get it?
Yeah.
Yeah. So you want to try to keep it as simple as possible for other people who are going to be working on it, and then also for yourself.
Okay.
Okay. Questions, concerns, cash, credit. Good. Okay, you ready to move on? Now that you guys know the balance equations?
Okay.
Okay. Okay. So now this also is going to start applying to energy as well. We need to take into consideration energy. We're not going to get too much into this. This is just kind of like my intro slides, kind of get you guys ready for it. Now, energy is basically defined as the ability to do work or to transfer heat. Okay, so there's energy could basically be put into a system, or it could be taken out of a system. So if we're putting energy into a system, it's called endothermic. If we're taking energy out of a system, it's called exothermic. Exothermic meaning that fire is being released and things like that, right? Okay, or heat is being released. Okay, so endothermic, you're putting energy into the chemical equation or into the system. Exothermic meaning that you're releasing energy. Okay, are you guys with me?
Yeah.
Okay, so like for instance, if we're burning butane, that's going to be exothermic. We're getting energy released, right? Because you guys stand next to, well, how many of you guys grill? I guess it's propane. The house. How many of you guys use a gas heater at the house in your fireplace? Anybody?
I do.
Like
Okay.
the stove?
Well, anything that's burning, do you feel heat if you stand next to it?
Mhm.
Yes.
You don't feel heat
Yeah.
when you stand to anything that's burning?
Yes.
You do. You do feel heat.
You guys,
And-
you're starting
unless
to
they
learn me
didn't-
here. I'm like, okay, we've got to work on these things here. Okay, so when you feel heat being released, you feel things burning, right? So that means that energy is being transferred. It's being released from that chemical reaction. Okay, so that's going to be exothermic. Okay, so kinetic energy is basically the energy due to motion, right? So if I throw a ball at you at real slow, does it hurt?
No.
No. So if I throw it at you really hard, does it hurt?
Yeah.
Yes.
Okay, it does, right? So you feel that energy, it has an increase in energy because the ball is being thrown to you at a higher velocity.
Mm-hmm.
Okay, so that means that we can kind of relate velocity to that kinetic energy associated with motion. Now, we talked about chemicals, like, or atoms and stuff. What do we say about like water or molecules? So ice, in the case of ice, what's happening to those molecules compared to
Slows down.
water?
Slows down.
Slows down, right? So those molecules are slowly moving, they're slowly vibrating, they're not moving too fast or anything like that. But when they're water, they're moving faster, right?
Yeah.
Yeah.
So there's kinetic energy that's going to be associated with states of chemical, right?
Yeah.
Okay, so now you guys want to start keeping these pieces of puzzles together, right? Because that's going to be important for all of the chemistry that you guys are learning. Okay, so we also talked about endothermic. What does endothermic mean again?
Entering. It's going into.
Okay,
That's
so that means energy is going into the system, right? So here, this is an example of photosynthesis. Photosynthesis requires the energy from the sun to get everything started, right? So we're putting energy into our system so that we can make sugar and oxygen. Okay, so photosynthesis. Simple, right? Not too hard.
No.
That's right. Endo, enter, exo, exit. Okay. So potential energy is basically the energy due to the arrangements of particles or location, right? So for instance, if we have a ball that's sitting above us, that ball has a certain amount of potential energy. As soon as I let go of that ball is able to drop, right? And then it becomes kinetic energy. Now, the thing about energy, just like matter, what you put in, you must get out. So it has to be accounted for. So if you're putting energy in, it has to be going somewhere or being stored somewhere within those chemical bonds. So like in the case here, we're putting energy in, but we're storing that energy up into those chemical bonds. And then if we eat that sugar, we can break those bonds and use that energy, right? So at the end of the day, what you're putting in, you have to get out. It has to be accounted for. It's like somebody had said, can you balance my checkbook? That's exactly what it is. We're balancing that checkbook, right? The money you put in, you must get out. Otherwise, you're going in debt, right?
Yeah.
Okay. Are we good? We're here?
Yeah.
We see?
Yeah.
Okay. Okay. So remember, we talked about energy, or kinetic energy, right? So E represents energy, M represents mass, C represents, in this case, the speed of light. We can also say energy, kinetic energy, is going to be 1/2 mv squared, where v is velocity.
Yeah.
Okay, so
Yeah.
Einstein basically came up with, it's called the Einstein theory of relativity. So basically E equals mc squared. He basically came up with that. And if we boil it down, all he's saying is that, energy is going to be equal to the mass times how fast you throw it. So if I have a really light cup, right?
Mhm.
And then, but I throw it really fast, that's going to give me a lot of energy, right? Or if I have a really heavy cup and I have a little, medium speed, and I throw it, that's going to also give me a lot of energy. So there's a proportionality associated with that energy, right? That deals with the velocity that we're using it at, and then also the mass. So for instance, if I have a penny and I drop a penny weighs very little, at a quarter from the same distance, and we assume that they get the same speed as they're dropping due to gravity, which one is going to have more energy associated? The penny or the quarter?
Quarter.
Quarter.
Why?
The
It
mass
has
is
more-
heavier.
Here.
It's heavier.
Because the quarter weighs more, right?
Yeah.
Because the quarter is more money, right? No, I'm just kidding. Because a dollar doesn't have the same effect, right? Unless it's a silver dollar.
Mhm.
Okay, so again, that tells me these are the laws of conservation. And chemistry deals, that is the bread and butter of chemistry, the law of conservation. I think one of the groups have this as their topic, the law of conservation, right? So we have the law of conservation of mass and energy. But at the end of the day, what you put in terms of mass and energy, you have to get out. Another way of saying it is that energy or mass cannot be destroyed or created, right? It can only be converted. You guys are with me there?
Yeah, that was one of the homework questions.
Right.
It was a trick one though, because it could have been the other answer, but the other answer was missing energy, I think. And it has to have both
Yeah.
mass and energy.
Okay, so here's the grand scheme. Now, and this is, again, the bread and butter of energy, of chemistry. So let's say here we have natural gas. So we're burning natural gas. What happens when you burn natural gas?
It dissipates
It
or
heats up the broiler or boiler.
Yeah, and it does that because it heats up that boiler, right? So it gets hot. It's transferring that energy, right? So we're having energy transfer through heat to warm up the boiler. So then the boiler does what?
bubbles?
Boiler boils.
Boils. Okay, the boiler
Oh.
boils. So what's happening to the water exactly? That's in the boiler.
Making a gas?
It's gaining
It makes it
heat.
a gas. So we're changing states, right?
Okay,
Yes.
okay.
Yeah.
So what
Yeah, okay.
happens? What's happening at the molecular level as it's changing states?
It's heating up. It's
Evaporation?
Bonds are being loosed.
kinetic energy.
Bonds are broken.
Are we breaking
Like
bonds?
that?
Wait. If I remember correctly, if I have water and I make steam, am I
Okay.
breaking any bonds?
Oh
No.
no. It's
No.
the same. It's the same.
What am I doing to those molecules?
You're making gas.
They are moving faster.
Oh yeah, I'm making gas. What did you say? What was that, Mary?
They are moving faster.
Moving faster, right?
Mm.
Like you guys did, right? So if you got on that hot beach, remember when we talked about that hot beach?
Oh,
So if
okay.
that sand is really
Yes.
hot, what do you start doing?
They
Running.
start running
You
fast.
start moving faster to the water, right? You don't just sit there,
Yeah.
you know? Same thing with those molecules. They're going to move faster. So they're moving
Okay.
faster, right? And by them moving
Yes.
faster, they make the steam. And then that
Okay.
steam comes up here, and then it turns that turbine, right? And then as we're turning that turbine turns to generator. And then the generator starts generating electricity. And we go and make electricity. So those electrons are being pushed through those lines. And then we're able to get lights. We're able to get our range. We're able to get our TV. Right? We're
Yeah.
good to go, right?
Yes.
Okay. At any point, did we create energy? Like out of the blue, it just magically appeared.
No, you transferred it.
We transferred, right? And that is the law of conservation. That is chemistry. Welcome to chemistry, guys.
Thank you.
Yeah.
Piece of cake?
Yep.
No,
Pass the class. Got an 8.
but it will be.
All done.
It will be.
Okay. So, are you feeling comfortable so far? Anybody not feeling comfortable? Be honest, it's okay. It's okay. It's still early. You know, I know you guys are kind of brushing off those cobwebs and stuff, and like, you know, those fractions.
I don't feel comfortable because I'm learning, so I wouldn't be comfortable if I wasn't learning.
Okay.
Comfortable because I'm learning.
Okay, that's good.
That's nice.
Okay. Now here's an opportunity to say something or forever hold your peace because we're ready to move on to the next set of slides. Are you ready?
Ready.
I'm ready.
Okay. Jose, you ready? Okay. He just gives me that look like he's disappointed, you know? It's like, that wasn't good enough. You got to do better. Okay, let's see. So velocity is equal to distance over time. Okay, so I know you guys are well aware of this. When we talk about distance, what type of units do we use for distance?
Kilometer, meters. Yeah, kilometer, meters.
Inches.
Can you use inches?
Yeah, kilometer, meters, inches.
Okay, feet.
Yeah, you got to remember we're
that's it.
Americans. We don't know about kilometers or meters. We know about some feet though.
Okay.
Feet. So inches, feet,
Centimeters.
centimeters,
Miles. Do we have that?
Yards.
Touchdown.
Okay, what about time?
Seconds, minutes, hours, days, years, months.
Seconds, minutes,
Milliseconds.
milliseconds,
Nanosecond.
nanosecond,
Okay.
Days.
days,
Years.
Months.
months, or years,
Mhm.
how about volumes?
Depth, right? That one.
Centimeter cube.
Centimeters cubed,
Meter cube.
meter cubed, feet cubed. What is volume anyway? Anybody?
Is it depth or no?
It's not
It
just
would
depth.
be
Depth would be like a distance.
length times width times height.
So it's length times width times height. Now, what does that really mean?
Can I also say mass per unit density?
Well, it's not density. Density is different.
Okay.
Density is,
Is it the space within that, within how long something is, how tall something is, and
this empty box, right?
yeah.
Empty box.
Mm.
is a volume, right? It's length times width times height. So you're right. It's that space that's being occupied by this empty box, right?
Okay.
Okay, so that's an example. What about the water that you drink? Isn't that volume?
Yeah.
Yep.
What units do we use for
Milliliters,
Millimeters.
milliliter.
milliliters? Okay,
Or liter.
Centiliters.
that means we use liters. We use
Centiliters.
Ounces, ounces.
ounces,
Centiliters.
centimeters. You mean cubic
Centiliters. No, centiliters.
Centiliters, centiliters.
Yes. Mm-hmm.
So we can
Units?
tell- We can
Units.
tell you're international because you're just talking about those centiliters and things like that.
Oh my God. I don't know there was even a difference actually.
What about
What about
gallons?
unit? What about
What about
units?
gallons?
Gallons.
Yeah, I
Okay.
was gonna say gallons. Yeah.
What about units?
What do you mean by units?
Units. Like, so if I was going to provide somebody insulin, wouldn't that be
That would be cc's.
okay?
So, and then when you're making reference to units, it could make when you're talking about units, it could be any type of unit. But
Well,
usually,
like 4 units. If they were going to receive some insulin, I would give them 4 units inside of the syringe.
yes, but that 4 units, what you're making reference to is cc's, right? Cubic
Okay.
centimeters,
Yeah.
which is this. Yeah.
Well, I mean, I guess on the needle it says both.
Yeah.
It says units and then it says the other.
Yeah. So units just make reference to what units you're making reference to, right? So unit. Okay. Okay. So these are some of the things that you guys you're going to need to understand. This is part of chapter 3. That was part of the exam that you guys got, whether you recognize it or not. You know, we're sitting there talking about how much of a drug that you're going to be adding to a person, and it's going to be based upon using those units and playing with those units. So you need to be paying attention to those units. And what do they mean? Do they represent volume? Do they represent distance? Do they represent time? Right? And then how does that relate to what we're talking about? Okay, so that's going to be very important for you guys to understand so that we can start using units to help us answer the questions. And sometimes, even though we may not necessarily remember things, if we look at those units, it can help us try to remember or start helping recalling some of the things that we may have learned in the past about those particular things, right? So let me give you an example. So we were talking about density. Right, Mary?
I didn't hear that actually.
I said we were just talking about density.
Okay.
Right? So if I told you that the units for density is grams per liter.
Dr.
Grams.
Henry,
Mhm.
Yes.
is this kind of math called physics?
Is this math also part of physics?
Yeah.
Yes. You'll learn that a lot of stuff that you learned in chemistry, it came from chemistry, and the physicists took it. Those bastards. No, but it's true. It's like a lot of the stuff that you're talking about, you may have learned in physics, you also learned in chemistry. You know, we share a general background. There's always been an argument about who came first, chemist or physicist.
Okay.
Okay, so like if we talk about grams is what?
Mass.
Mass.
It's mass, right? So we know grams. Grams is mass. So density is mass over what?
Volume.
Mass over volume. So if I'm taking a test and they gave me something like this, they say 1.5 grams per liter, 1.5 grams per meter, 1.5 grams per second. Which one do I know is correct?
Okay, the
Or
grams
density.
per liter. The grams per liter.
How do I know that?
Because of the volume.
Because you know the formula.
Because I know the units of volume. Volume is either liters, cubic centimeters, cubic feet, ounces, gallons, centiliters, right?
Okay.
I know that if I have grams per meter, right, that's mass over distance.
Mhm.
If I know if I have grams over seconds, that's
Mhm.
mass over time. So I know that
Yeah.
these are both wrong instantly,
Yes.
right? Makes sense?
Yeah, it makes just.
Okay.
Yeah.
Okay. So let's keep ready. We're gonna stop here. So there's no lab today. I'm gonna go to the lab room because I promise you that there'll be somebody who's gonna show up and say, "Oh, I'm here for the lab," right? So, okay. So if you guys have any questions about anything that we talked about today or anything that's going on, you can meet me in the lab room and we could chill out there and we could talk about